Hello, my name is Tomctutor. Yeah, that's me. This is the last video on the differential of the inverse functions. The first three videos we set up some theory as to how you actually find these differentials. So I'm going to have some practice here with some actual problems, just to show you how we use the theory. But before I do that, you may have call this question 1. Okay, and I'll just give you the problem. So we have f of x is x cubed plus x plus 1. Okay, and we need to find the gradient of this function, the gradient of the inverse function at x is equal to 1. Okay, so that's the question. Well, you might be tempted to use my technique here and blah 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 and find the inverse function, but it actually doesn't ask you to find the inverse function. It actually doesn't even ask you to find the actual derivative of the inverse function either. It just asks you to find the value of the gradient, which is just a number. So there's a formula we use here. I'm not going to give any proof or anything, I'm just going to state it. And the formula is that the derivative of the inverse function at a particular point, x is equal to a, okay, is given by 1 over the derivative of the inverse value of the function at a. Okay. Now we can use this here to solve this problem, but there is a condition. We have to check certain things. First of all, the function f of x has to be differentiable. So the f dash of x must exist. So that's the first requirement that we have to check. It's a polynomial. It's a order 3 polynomial in the reals of x. Therefore it exists and it's differentiable. So there's no problem there. The second condition is that the differential has to be basically not equal to 0. Otherwise, this lot here will have a denominator of a 0. So that is the f dash of x must not equal to 0. Okay, this actually is a very subtle point here. This requires that the function is always increasing or always decreasing if you think about it, because if that's a graph of a function, if somewhere it is say got a 0 gradient, then it's increasing and decreasing again. So that means that the so-called fails the line test, as we say. It's many to 1. So that means when we take the inverse function, we'll have a value here, and it will be bringing us to. It won't be the inverse function. It's a bit like the square root. It's got a positive and negative. It's not a well-defined function if that happens. So that's why we have to do this test to make sure it's basically a one-to-one function that we have here before we can use this. So we'll have to check this condition as well. So f dash of x is just simply 3x squared plus 1, and I hope you can see that that is always greater than 0 for all of x. Okay, because it's a sort of irreducible quadratic, so alright, so we're then happy that we can use this. We satisfy the criteria to use this little formula. So here we do x is equal to 1, so we put a 1 in there. We've got the f dash of x, but we need the value of f minus 1 of 1. we have to work out what out that value is. If I put 0 in here, I get 1. So f of 0 is equal to 1. Okay. And I know, because of this condition, that there's no other value that I put in here to get the 1. Okay, that's pretty important, that wee step. So the f minus 1 of the 1, just swap these coordinates about, is 0. Okay, so at the end of the day, my answer to this problem, the d of x of f minus 1 of 1, the gradient of the inverse function at the point x is equal to 1, is equal to, if I put 0 in here, because that is equal to 0, it's just f dash of 0. It should really write f dash of 0, but I'm running out of space. So f dash of 0, well, okay, let's put it in like that. It's 3 0 squared plus 1, which is equal to 1. And that's the answer. So the gradient of the inverse function at that particular coordinate is just 1. Okay. So anyway, I thought I would emphasize the method you use to actually find an actual gradient value, the tangent, the slope of the tangent, etc. Okay, thank you. Now we move on. The next problem, question 2, is a very simple problem, really. Sorry, I've lost my pens here for a moment. Question 2 is if we have f of x is equal to x squared plus 1, basically find the differential function of the usual d of x of f minus 1 of x, okay? That's the question, alright? That's what all these questions are. So if to find the differential of the inverse function, well, this is a very simple function, so we can do it quickly by just finding what the inverse function is. So what we normally do is we set y is equal to x squared plus 1, but y minus 1 is equal to x squared, so that will give me x is equal to the square root of y minus 1. Okay, so the inverse function of this, f minus 1 of x, is just simply the square root of x minus 1, which is x minus 1 to a half power. So the gradient of that, the d of x of f minus 1 of x, which is what we have to find, is just simply 1 over 2 times the square root of x minus 1. Okay, and that's the answer to that problem. So I've not done anything really other than I've established what the inverse function is here, and then I just simply differentiated it, which is probably the best way to go if you can, really. Alright, fair enough. Not too difficult. So here I've got question 3, and this is a bit more subtle. Given f of x is equal to e to the ax, okay, show that the differential of the inverse function, df minus 1 of x dx, is indeed equal to 1 over ax. Okay, now I know what you're thinking, you guys. Well, the inverse function, right over here, the inverse, where's trapped, so the inverse function, f minus 1 of x here, is just simply 1 upon a times log n of x. Because if I put that guy into there, okay, that would just basically return x. Okay, and that's how I know that's the inverse function. So we have the log n here. So as in the previous example, question 2, why don't we just differentiate that? So the answer to the question, the d of x of f minus 1 of x, okay, is just simply 1 over ax, and that's the answer. Not good enough. Why? Because all I've done here is I've differentiated this guy to obtain that. Okay? But I haven't shown that that is actually related to that. The question is asking for the differential of the inverse of that guy with respect to x. And I've picked some other function, this guy, and I've shown that differential of that is equal to that. Just because differential of that is equal to that doesn't mean that the differential of that is equal to that. Okay, in general, it's sort of bad. It's bad to do that sort of thing. You have to sort of go directly from there to there. Now you might not agree with that, but so let's see how we can get around this little dilemma. Not knowing the log n of x is indeed the inverse function. So the way I suggested that you do this is we would set up a function g of x. So I would let g of x is equal to the f minus 1 of x, okay? Right? This is from, I think, my last video 3 there. And so we have EAG is indeed equal to x. Okay? So I'll put a g in here now. Because that's the inverse function, so if I put that into the original function, I get f of f minus 1 of x, okay, which is obviously just x. So we covered that in the other video, so I'm not going to go into it here. And then I differentiate all with respect to x. So I have AEAG times g dash x is the differential of the right hand side is 1, so g dash x, which is indeed what this is, okay, is equal to 1 over a e to the ag, okay. But what is e to the ag? Well, e to the ag from here is just simply x, so it's 1 over ax as required. So that finishes the proof. Notice there's no logs in there. Okay, so no other function's been introduced. Okay, so I don't even have to know anything about the differentiability of the log n function. And I've shown that directly. Okay, so that's what I was trying to emphasize. Right, okay, so we're sort of getting on top of all this now. But questions can get a bit tricky. Okay, so here's the next question. And we're given that, given ut, some function of t for time, I assume, is 1 over t times 1 plus t. Show that, so there's two parts to this problem. Part A, show that ut is, that's ut, is equal to u, that is, it's equal to its own inverse. Okay, so how are we going to do that? Well, if ut is equal to u, that means that u of u minus 1 of t should equal u of t should equal t. Okay, because that's by definition, you know, put the inverse function in, will return the independent variable t. So all I have to do is to put the whole thing, substitute it in for t. So that becomes minus, it's a bit tricky this, and do it in my mind. So it's minus 1 over t times 1 plus t, so that's the top part, all over 1 plus minus t over 1 plus t. Okay, so I've just replaced the function into there. Okay, so when I do that, I can cancel out there and multiply that by 1 plus t here and get rid of that, and that gets rid of that. Minus times minus is positive, and I have then 1 plus t minus t at the bottom, so the whole lot just becomes 1. So all I'm left with is that single t, so that is equal to t. So since that, then that can be if and only if the inverse function, that guy there, is equal to that. Okay, so we have indeed shown that ut is equal to u minus 1t. However, this is not really about inverse functions as such. We're working in a calculus, so you should be able to do this anyway. So I'm not, I shouldn't even waste the time doing it. But anyway, we've done it. So we know that, just to emphasise, we know that u minus 1 of t is equal to u of t by part A. Okay, so we're happy with that. But then we have to find the derivative of this function. Well, because of this relationship, part B of the question, okay, we have that du minus 1 of t dt is just simply u dash t. Okay, so all I have to do is differentiate the function itself. So when I do that, I will end up with 1 minus 1 over 1 plus t squared. I think that's the answer. Okay, so we just differentiate that by the quotient rule and we'll end up with our answer. Okay. Right, so we're doing well. I have to rush on. The next question. So you see a lot of these questions aren't that really difficult. I'm looking for the next question. So let's say we have u of t is the sec t upon a, and we have to find the usual differential of the inverse function. So what we do here is we say let v equal to u minus 1 of t. So v of t, I should say. Well, doesn't matter. Okay. Let v equal the inverse function. That is, if that's the case, then t has to be equal to the sec of v upon a. Okay. So I've got that. I'm using different variables here in my notes, so it's a bit confusing. And what we're actually after is dvt over dt, which is really 1 over dt divided by dv. Okay. I mean, you could say that's v dash t, which obviously written like that is that. And this is actually what we've done in the other video, so I'm not going to waste time to justify what I'm doing here. This is what I'm doing. Okay, so I'll just rub that out. So we differentiate this function. Okay, so when I differentiate that, I'm going to get like t dash in terms of v. It's a sec function, so it's 1 upon a times the sec v upon a times the tan v upon a. Okay, because that's the differential of a second function. And then of course we just reciprocate this, which will give us a over the sec v over a, tan v over a. Now at this point you should look up here Okay, and I'll change the colour here. Hopefully it'll be clearer. And that's t there, okay? So we're replacing that by t there. But we've still got the tangent, but we've only got the secant. But I hope you know that, that the tangent of any angle theta is just basically the sec squared of theta minus 1. Okay, so that's the identity that we're using here. So I can cross that over and put in the square root of t upon a. Remember, where am I? The angle is t upon a. So it's t upon a squared minus 1. Okay, because I'm just taking the secant, and the secant of the angle. Have I got that right? Wait a minute, I think I've got that wrong. Sorry, my apologies. I'll go back. The tangent of v over a. That's v over a. Okay, it's just simply the square root of the secant, and the secant of v over a, so it's just t squared minus 1. Sorry, so it's t squared minus 1. So our answer, which is v dash t, if you like, in this particular case, but I'm not going to write that down there. I'm going to write what the answer is. So it's du minus 1 of t, because that's what they asked in the question. So I'm not going to give the answer in terms of some other variable, which is not in the question, is equal to a over t times the square root of t squared minus 1. Okay? So that's the answer. Given that, we've defined the derivative of the inverse function. Oh yeah, and this, we're running short of time, but I think it's important to put this last example in, so that just in case you got a question like it. It's basically exponential. So I'm going to make some assumptions here. Yeah. So we have f of x. I can't remember if I've upped this question number. Anyway, f of x is equal to a times cos x plus sin x. Okay. Now, what not to do is to expand that as e cos of x times e sin of x. And then you'll end up with two functions, and then you'd have to differentiate and do the product rule. Because the reason is because we're going to have two functions in x, and we have to find the inverse function, and I'm not too sure basically how to do that. So you might say, stuck at that point. Okay? Not really. Because in this particular instance, we can just use the wave equation, and the wave equation gives us that cos x plus sin x is identical to the square root of 2 times the cosine of x minus pi over 4. Okay? And that's good, because we can then replace that exponent by a single function of x. So what f of x now becomes simply e to the square root of 2 cosine x minus pi over 4. Okay, and just to remind you that this function isn't a gently increasing function. If I plotted this function, it would be something like that. Okay, so with that sort of behaviour on it. So it's sort of periodicity involved here. Okay, so many to one sort of mapping. Anyway, you know what I mean. You have many to one on the map. So anyway, I digress. Okay, so we have a direct function here. So the way, as I said, to do it was to invent a function. So let g of x equal to the inverse of x, okay? And once we do that, of course, we have the x is equal to e square root of 2 cosine g minus pi over 4. Okay, and this is my function of g, if you like. Okay. Notation here. I've already stated what it is. It's g of x. So if I differentiate, sorry, that's x in terms of g. So x dash in terms of g, as we differentiate that, and I get minus the square root of 2 sine g minus pi over 4 times exponential, all this stuff, okay? And then what we do, of course, is we just take the reciprocal of that, x dash of g, and that is 1 over minus square root of 2 times the sine of g minus pi over 4 times this exponential here. Of course, this exponential is this lot. Sorry. This exponential is basically just x, okay? So I can replace all that by x itself, alright? That's a g there, sorry. So, I have to get rid of this sine g thing. But the cosine g is given up here. If I come over here to the other side of the board, I'll just change colour. So we got a colour here. So I can now write what g of x, what this sine thing is here. And to cut a long story short, what I get is that the sine of g minus pi upon 4, okay, is actually, because I take the log of both sides, square it, take the square root, etc. You should end up, I believe, give me a second here, the square root of 2 minus the log n squared of x all over the square root of 2. Now don't jump on me if that's wrong. My notes are using different symbols, etc. But anyway, if I put that in here, I get my g dash of x. Or as I said before, which, you know, that is the reciprocal of that, is the d of f minus 1 of x dx. Best to write it that way, okay? Because that's, we don't know what g of x is, something I invented. It's not in the original question. So if I'm right, the answer should be minus x times the square root of 2 minus the log n squared of x. So that is the differential of the inverse function to that. Okay, so that constitutes this video, and I'm sorry it's taken so long. Had to skip through a few things, but hopefully it's been useful to you. I will be doing another set of videos, and in this other set of videos I shall be looking at the integration of inverse functions, sort of the integral of f minus 1 of x dx, both in the indefinite form and in the definite form, and also be looking at limits. So we'll have the limit of x sort of goes to infinity, this sort of idea. So and that will tie in with this obviously, and that all constitutes the calculus of the inverse functions. So keep coming back to this channel, and you should be, in the near future, these other videos will be up. Please submit any comments down below, and welcome any comments, criticism at all, good or bad, the ugly, and hit the button, the like, or the not like, whatever you like. Okay, so see you again. Right, bye.